So what we'll do today is we'll kind of again quickly revise or go through what we discussed in the last class, and then go into the two papers related to level shifter design in a little bit more detail. So basically, the topic we were looking at is multi-voltage design, where you have a chip, and in that chip you have different portions of the chip which are running off different supply voltages. And why do we do that? As you know from the power dissipation equations, if you recall, voltage is one of the key parameters both for dynamic power consumption as well as static power consumption. So if you reduce voltage, you reduce the power consumption. Also, reducing voltage reduces the helps to reduce energy also, especially the dynamic energy. So the reference for this chapter for this topic is this chapter 3, low power methodology manual. And you have this typical scenario where you can have multiple blocks in a chip, and certain blocks like memories, it's very hard to scale down the supply voltage because the memory cells are not very stable at very low supply voltages. So you want to keep them at a higher supply voltage, but certain other blocks you can reduce the supply voltage. Another kind of important portion of the chip where you cannot reduce the supply voltage is there are two places. One is the IOs, because you might have to connect to chips outside which use certain standard supply voltages. So at the IOs you need to somehow be able to transition from a inner lower voltage at the inside to a higher voltage outside. Also, another area could be mixed signal interfaces. Maybe you have some analog blocks and so on, and again and those have digital interfaces, and again there you might have to have low to high voltage interfaces. So when we come down to voltage scaling, that is when what are the different ways by which different techniques for changing the voltages or scaling the voltages. So the first is static voltage scaling, where during design time you a priori decide that you're going to have certain fixed voltages for different blocks, and you arrive at those voltage numbers based on some analysis you have to do for power versus performance during design time. Okay, so based on that you say, okay, I'm going to have these different voltages, and those are fixed and kept like that. So when the chip comes back, you have to basically have voltage regulators or some way of generating those specific fixed voltages for each of these blocks and provide it to them. In the multi-level voltage scaling, what you have is you have these blocks, but maybe some of the blocks, the voltage levels can be a couple of different discrete values depending on the power state the chip is in. So, but there will be a very small number of voltage levels corresponding to the different operating modes of the chip. In the case of dynamic voltage scaling, within a given operating mode, power mode, the voltage level of a particular block could keep changing with time intentionally. The design would be such that you keep on adjusting the voltage levels based on the different workload requirements. And then finally you have adaptive voltage scaling, where the exact voltages used are determined on a per chip basis using some kind of feedback control technique. So whenever you have these different voltage domains, you have to, and you are exchanging signals between them, you need to do this level conversion. So that is one of the challenges, and one of the additional things you need to pay attention to. Second is the library cells. The digital designs, you pretty much basically, most of the digital designs are done through synthesis. You do your design in RTL, then you have a standard cell library to which the synthesizer synthesizes to. So the libraries have to be characterized for these different voltage values at which you want to use that block. And and also when you also do the analysis of your design, when you have signals going from one voltage domain to another, and you are essentially you have a clock on the voltage domain 1, the transmitter voltage domain, which launches a signal. It goes through that voltage domain, goes across the interface, gets into the other voltage domain, and then gets captured there. So now you need to do timing analysis across the entire path to ensure that your max and min timing constraints are met. So what that means now, if you have multiple voltages on the source on the transmit side, multiple voltages on the receive side, then across all combinations, you need to characterize and ensure that you meet timing. So it kind of increases the complexity of timing analysis also. And then you of course also have to do floor planning and power planning. So we kind of want to make all the cells and the domains, the logic, all the blocks which use the same voltage contiguous to each other, so that you can very easily provide power to them. And similarly, you'll have to kind of plan on where the power pins are, what is the power grid, etc. So that also has a ramification on the packaging, because the pin positioning and what you do on the package and the PCB has an impact based on what you do out here. And finally, at the system level point perspective, how you bring up these different voltage domains, how you shut it down. So you have to kind of pay attention to that, so that your system, your design doesn't get into some kind of weird deadlock type mode. So if you look at the level shifter, you basically have to ensure that you have good slew rates for the signals. And having good slew rates is important, because one of the things is that if I have a logic gate and the input to the logic gate is changing very slowly, it has a very poor slew rate, very slow rise time or a fall time, then that logic gate will consume a lot of crowbar current, because for a longer period of time both pull down and pull up stacks will be high. So it's not good to have very slow rise times or fall times. Secondly, when you have very slow rise times and fall times, any noise while the signal is transitioning across the logic trip point of the gate to which it's being fed to, at that time, say there is a little bit of noise coupling, then that translates to an equivalent error or equivalent jitter in the timing. That is, when exactly it crosses the trip point is influenced by the rate at which it is going and the amount of noise you put in. For the same amount of noise, imagine that I have an ideal step. When I have an ideal step which has infinite rise time, if I put a little bit of voltage noise at that step, it's not going to change the time position of the step. It's just going to change the magnitude of the voltage step, right? It doesn't affect the time. Whereas if I have a very, very slow edge rise time, if I put a little bit of voltage noise, I'm shifting the whole edge up or down. So the point at which it intersects the time axis at the logic trip point voltage value, that time will essentially fluctuate a lot depending on the amount of voltage you put in. The exact amount of fluctuation will be given by the slope times the voltage noise, or voltage by the basically depending on what units how we are defining the slope, it's related to the slope and the voltage noise. So the timing noise is essentially proportional to the voltage noise as well as the inverse of the slope. So because of that, you need to ensure that you have good slew rates. And also, you can, for example, when if you are going from high voltage to a low voltage domain, sometimes you might say, from a functional point of view, you might not, or power point of view also, you don't need explicitly a level converter. You can directly get the signals in. But then you have this complexity that you don't know which logic gate the signal will be feeding to from the high voltage domain. So that means when you want to do analysis, you have to have characterization of every logic gate, because you don't know which one will be used at the interface boundary for the input voltage and the high voltage and the voltage for which the logic gate works. So that will lead to a lot of characterization. So you might want to put an interface cell where you absorb the characterization complexity, and all the other cells are characterized for whatever voltages they are supposed to run at. And of course, low to high, we need to have to eliminate the crowbar currents. So the high to low shifter is very straightforward. It's just a pair of inverters which are driven by the low side supply voltage, VDDL. Okay, so this is the symbol of this structure out here, and you have it basically introduces a buffer delay, and that's kind of it's very simple and straightforward. The low to high shifters are a little bit more complex, because I can't, if I were to use this for low to high, then what is the problem? The problem is that when my input high, just imagine now, just ignore this symbol of VDDL, imagine that this input voltage was from the low side. Then when I use a simple inverter which is driven by higher supply voltage, what is the problem? The problem is when my input is high, that high voltage is not turning off the PMOS fully. So I can have a lot of static current going through this. So I need to do something more than just putting a simple inverter, and what is done is this kind of what is called a half latch, where you have a cross couple PMOS, and the cross couple PMOS essentially helps to pull up the PMOS completely to shut it off, so that you don't have the leakage current. So how does it work? Let us say that this guy is 0 and this guy is 1. That is the initial state. Now when the input comes, as that it turns this on. So the input comes and you generate the input and its complement. So you might, for example, do away with one inverter. You don't need both the inverters. You might just take one inverter and drive it out here, and then take its complement. I mean, you have the signal connected directly here and its complement. You just need the signal and the complement. So here they have provided an additional level of buffering. So you have the say you turn this on. So what that does is it helps to start pulling this node down, right? When this node is high, that means this PMOS is on. So you start pulling this node down, and once this node comes down sufficiently to turn this on, what that does is it starts pulling up the opposite node, and then it weakens this PMOS further, helps to pull this down even faster, and so on. So it's basically a positive feedback which helps you to latch the signal value out here. Okay, so this is how this particular low to high shifter works. Now this works very well when the voltage levels, the high and the low voltage levels are not too far off. Then this is good enough and it does the job. The problem comes when the voltage at the low level is extremely low, especially down close to the subthreshold regions, where the drive for the PMOS becomes so weak, because the PMOS gate, because these voltages of these inverters is just VDD low, which is say near subthreshold or near threshold, 200, 300 millivolts. Whereas this high voltage could be high, the nominal voltage 1 volt, probably even 2 volts for the IO interfaces and so on. So then what you are expecting is this NMOS transistor to kind of overcome the drive of the PMOS. PMOS is turned on fully because it has a full high VDD across it. Whereas the NMOS, when it turns on, has just the near threshold, the voltage of 200 or 300 millivolts. So for those kinds of conditions, we have a problem with this particular topology, and that's what we'll see later, how various couple of different approaches people have used to make that work. So of course you need two different supplies, and you need to separate out the wells for the PMOS. That means what we are talking about, the PMOS is here and the PMOS is in these two inverters. So you need to have a separate P well for them. And there is quite a bit of delay penalty, especially when the voltage differences are high. And if your design allows you to, if your architecture is such that as soon as I enter into my other voltage domain, there is your clocking, you're kind of capturing it in a flop, then you can merge the level conversion with the flop using some kind of a sense-ham type structure. So where do you place these level shifters? You basically, it's kind of advantageous to place them in the receive domain. For example, here I don't need to route an additional power supply. I just need to send the signal from here to here. Whereas if I were to keep this, so this is the high voltage domain, this is the low voltage domain, 1.2 and 0.9. If I put the level converter here, then this level converter VDDL has to be supplied. I have to route one's VDDL signal from there. Whereas if I put it here, I just have to route the signal. So this is kind of, seems to be more convenient to do it this way. So here we have three domains, 1.2, 0.9, both of which are embedded in a 1.1 volt domain. Now when these two are very far apart, you might have to put a repeater, right? When you have very long interconnects, the delays might be very large, and so you have to put repeaters to reduce the delay. And when you put repeaters, you have an issue of what voltage to use for the repeaters. The repeaters will be in the 1.1 volt domain, whereas the signals are in the 1.2 volt domain when they are coming in. So which means you need to also route the high VDD to those repeaters. So this is where the floor planning also comes in. If you had floor planned it such that you didn't need a repeater, you wouldn't have to deal with this problem. But sometimes you cannot get what you want, so you might end up with having these two very far apart, and you might need a repeater, in which case you have to deal with the power planning issue. How do I get the VDD edge to this? How do you route it? Is it like a signal? And importantly, it has to be part of the methodology, the tools that you have to be able to use the tools and guide the tools to use these kinds of uh, things.
We can use different metal track, metal layers itself, right? So that isolation would be very best.
Yes, absolutely. So you have to use, the thing is, it's not these are not what I would call some fundamental road blockers or something. It's more, especially in digital design, you cannot want to, if you're doing a custom design, right? There is no problem at all. You just, you know how to do a layout of an inverter. You can always, how to do your routing. You can always get one signal and do it, right? But you can't keep doing it, for all the designs, all the chips, all the times, right? So you need to have a way by which this process is incorporated into the tool flow, and you have to basically use the different layers and all that so that you don't short the two VDDs. So that you have to do that, and importantly, you have to make sure that the current supplied, the VDD wiring, is sufficient to handle the current which is required to drive the buffer. So that is basically one of the key requirements for a power supply, is that power supply routing is that it should be able to supply the currents without too much of a voltage drop in the impedance of that wire. So low to high placement, again, in this case, no matter where you place this, whether you place it on the high side or on the low side, this cell you have to route one or the other wires. You might want to there is kind of some advantage to putting it on the high side, because the VDDL side of the circuitry will not consume too much power, because it is very low voltage. It doesn't consume too much current. So the requirements on the power supply, the requirements on the power wire design will be much less stringent. So from that perspective, it makes sense. Also from a power consumption perspective, because if you end up putting a repeater here, then that repeater is also driven off a lower voltage. So again, power consumption will be lower. So there is some advantage to putting the level converters in the high voltage domain, or in the receiving voltage domain, whether it's high or low.
So in the previous slide, previous one, here when we are using these buffers, can we use this? Can we place the shifter in this 1.2 volt domain, because we are anyway routing this power supply VDDH, because the repeaters, in that case repeaters we can give VDDL supply so that they can consume less power.
Okay, so this is a good good comment from Arnab, where can we put the level shifter, from a power perspective, why not put the level shifter in this example from the receive side to the transmit side? The reason is that, and whether we put a VDDH or not, the advantage of that is that the wiring capacitance and the power required to drive the interconnect will be lower, because I am going to be using a lower voltage supply to drive that. And that is true, yes. It's just that then you have to route a VDD. Yeah, in this case anyway I have to route a VDDH, but if I were putting a repeater, why not put this and route a VDDL? Isn't, that seems to be a better option. So the question is, if you were to route these low voltage signals around long distances, won't they be vulnerable to picking up noise? Basically, especially if these signals are going through high voltage domain, there will be signals nearby which are switching high voltages, and they can couple in and affect that. And the answer is yes. And you have to basically ensure that the signal integrity is maintained. Now, the problem of signal integrity is there whether even without level conversions and so on. If you recall from the last semester, you have this problem of crosstalk, right? So that is the problem, and so typically there will be a separate integrity check, signal integrity check, which will be run. You have to do that signal integrity check once you're placed and routed the design to ensure that the crosstalk and coupling and all that will not affect the functionality of that. So that has to be done anyway.
So lower voltage can also mean lower drive strength can be. So if the VPD is fed by a low voltage, then its drive strength will be lower for driving the same amount of wire to the circuit domain. So size will have to be increased again.
Yes. So the
It will be longer for VDD. It will be on up to the 1.2 volt domain. Here VDH is up to only the half of it, right? Where VDH will be up to the 100.
Okay, so we have points and counterpoints. So we have a nice little debate going on as to whether we should, in the case of this particular example, is it better to leave VDDL here? I mean, this level converter here, or shift it out here, right? That is basically what we are talking about, and the arguments against shifting it out here is that if you do shift it out here, the problem is that the speed of the signal to drive this from here to here will be degraded because you're using repeaters or inverters which are driven off the low voltage supply, right? So that is one kind of argument, maybe not to push it out here. The second argument someone also raised was the length of the wire for routing VDDL will go up. Now that I would say is not really a big deal. So that is not really any, because the problem is more once you have a method of drawing out a VDDL as a single signal in some sense, the extra length you go doesn't matter because you can easily deal with that by increasing the width of the wire and so on. But the point of speed being impacted is definitely there. So it's a trade-off, speed versus power consumption.
Actually, it is going through a 1.1 volt domain. So maybe that crosstalk can be a factor. That's why we are not lowering the voltage. Because the crosstalk from 1.2 to 1.1 would be approximately 0.1, and that from 1.1, if we were to transmit it at 0.9, then it would be around 0.2.
So the question being asked is, or the point being made is, would crosstalk also be a consideration in deciding whether to keep the level shifter on the right side or on the left side in this example? And I would say is no. I would say, because the reason is that firstly, crosstalk is anyway a problem you have to deal with, and you have to see how to kind of mitigate that. And there are known ways of dealing with that, which is just put shields. You put shielding, you make sure that the high signals which will couple in are not close by and so on. So those are kind of things which are standard practice, and you can do that. So it will just come down to this power versus speed versus whether I need to use a VDDL, whether I need to do some extra work on routing the VDDs or not, and that will decide where I'm going to place the level shifter. The other thing you kind of want to do is that, so the general kind of heuristic is to place the shifters in the receiving domain, and the low to high shifters can be quite slow, especially when the voltage differences are large. And so from a design, when you are doing the design, if you are aware of that, then you can take care of it somehow by your microarchitecture. That means how you pipeline your design, where you put your flops and so on. If you don't do that, you do your design, it goes through the synthesis, place and route, etc., and then you might find that you have a timing problem, you have to fix it. So it can be a extra loop to deal with. And finally, you want to, you know, if your voltage relationships are fixed in terms of direction, that means one is lower than the other, you can maintain that relationship, life becomes much easier, and that is not that hard to do. So you have also the issue of clocking, because you need to remember the requirement of the clock distribution system is that the arrival of the edges at these flops, wherever the flops are in a particular synchronous domain, the arrival time should be same. That means there is no skew. So when all the voltages are the same, then it's just a standard clock tree design problem, where you have to ensure that the delays through from the source to each of the leaf nodes of the clock tree are balanced or equal. The complexity becomes there's one layer extra of complexity when the domains are different voltages, because now for the clock also you need to have level translators, right? And the delays of those level translators will be different across different domains, so that has to be taken into account when you do your design like this. And also, if the voltage levels keep changing, maybe either due to your multi-level voltage scaling technique or due to dynamic voltage scaling, then again you have a problem. So one way to deal with this problem is to not do your design like this, right? I mean, you can try to put level converters and do all your things about balancing, but the other thing is to say, take a step back and look at the architecture of your design and say, okay, no, I don't want to have this kind of a synchronous clock domain across different voltage domains. And see if you can change your design or partition your design in a way that your synchronous domains correspond to voltage domains. And then when you go from one voltage domain to another, you apply the techniques which are required to cross clock domains, right? Now you might run them off the same clock frequency, but the phases could be different relationship. But again, you can use techniques. They are pretty well known techniques of how to cross and hand over signal across different clock domains. Now, if you can do that, that will be the most modular and robust way of doing your design. And that's what I would kind of suggest. I would try to do it that way, so that I don't have to deal with this clock tree synthesized across multiple voltage domains, and it kind of makes life much difficult, and the system is not secure.
How can we take care of these different domains in Verilog coding? SDL we can't take care of different voltage domains.
Actually, if you look at the textbook, which the reference I've given in the last appendix, you have a look at that. You go through that. So there is a UPF, something called UPF, Unified Power Format, I think. So that allows you. So it's a standard way of specifying aspects in the RTL related to power gating, level, where to put level shifter, etc., etc. So these are additional statements you introduce in your Verilog code, so that the tool which then synthesizes it knows what to do. So you can kind of go through, just browse through that appendix, and you'll get some idea about that. So floor planning, we already saw that you want to put all the blocks of the same supply together, so that you can easily route the power grids, you can isolate them, and you can also allocate pins, etc., to that easily. And system design, especially whenever you have multiple power supplies, the sequencing of power when you bring up and bring it down is kind of something you have to pay attention to. So now let's look at a couple of level converter designs which basically deal with this issue of level conversion when the voltages on the low side are very low. Now, why is that important? That is important because now you see that many applications are coming up where power is really critical. Okay, these are applications, for example, biomedical sensing or sensing, essentially anything related to sensing. And these are devices which are embedded all over the place, and having batteries or power, supplying power to them becomes a problem. So you want them to have run of very low power, so kind of like your watches. So one of the approaches is to actually to get very low power, so that either they are run off very small but tiny batteries, or they can run out of power harvested from the ambient through solar, or thermocouples or vibration and so on, so that you don't need to deal with batteries for them. Now, one of the key techniques is to reduce the voltage to very low levels, down to few hundreds of millivolts. So this is near the threshold voltage of the transistor, so that's called near threshold computing. But no matter what, you will have a chip where you will have some blocks which are running off higher voltages, especially blocks which are connecting to the outside of the chip. So now your level conversion problem becomes even harder, because what you have is basically, if you take your latch based level converter, which you see out here, let me zoom in a little bit. So what you have here is, so can you see this figure, everyone? Okay, so this is the same latch based level converter. So now I'm basically looking at this paper called Energy Efficient Sub-Threshold Level Converter in 130 nanometer CMOS by Wouters and the group. I think they are from, they are from University of Virginia. And so they propose a particular design for solving this problem. But before getting into that, let us look at the problem which we have. Right? Why do we need something different from this standard thing which we saw? The reason is that here, when you look at the condition when M3 is on, that means this node here is high. Okay, this node is high here. And you want to bring this node down. When input V low goes high, M1 turns on and is supposed to bring this node down, right? But you have to fight against the PMOS M3. If my input voltage is maybe 200 millivolts or 300 millivolts, and my VDD to which I want to level convert to is at 1 volt or 1.2 volts or even 2.5 volts if I'm the IO, then my PMOS is very strongly on. It is in the super threshold region. And this weak NMOS has to overcome that PMOS, and it will fail, it will not work. Okay, so it will just be incapable. I mean, you have not even turned on the NMOS, practically speaking, and you want to pull this thing down, and that is where we have a problem. So as the levels between the transmit side and the receive side the differences become very large, this kind of a structure doesn't work very well. So how do you solve this problem? Well, firstly, you recognize what the problem is. The problem is that I am unable to overcome the PMOS. PMOS is turned on too hard. So what can I do to weaken the PMOS, basically? Or what can I do to strengthen the NMOS? So one approach to strengthen the NMOS is to use larger sizes. But we'll see, actually it turns out in the subthreshold region, the drive strength drops exponentially. So the size also grows up exponentially if you want to match the drive strength or the PMOS which is in the superthreshold. So it just doesn't become a practical solution. For small voltage differences, it's okay. 1.2, maybe 0.9 to 1.2 or 0.8 to 1.2, you just upsize the NMOSes and deal with that and solve the problem. But subthreshold, it doesn't work well. So then you say, how do you look to weaken the PMOS? So there are various ways of weakening the PMOS. So this is one way where what is being done is diode connected PMOS. So the idea here is that this PMOS gate is not so let us see what happens here. So when input is 0, okay, M1 is off, M2 is on, okay, and say the output is low out here, and when M1 is off, this node rises up to VDD, so M4 is also off essentially. So you have M4 and M2, and they are kind of basically off. Now when input goes high, you are essentially uh, the M3 is not fully on, unlike in this case. In this case, the M3 is fully on because the gate of the M3 is at ground, whereas here the gate of the M3 is also close to VDD. Depending on, if you give enough time, it will go reach VDD or very close to VDD, otherwise it will be about a threshold below VDD. So you are not pulling, and this is not as turned on as this, still in the just near in the near threshold region, and so this structure is able to work properly even when the input voltage is close to subthreshold. But the problem is when the input is high, M1 is on, the output comes down, okay, but it doesn't go all the way to ground because of this diode connected PMOS. So you have two on devices, M1 is on and M3 is also on. Of course, M1 is on weakly in subthreshold, but still you have a static power consumption in this line. So that is why this is not such a good design from a power consumption perspective. So really the problem is that we have this problem where our NMOS strength, which is, even when I'm turning it on, it is much lower than the PMOS strength, because PMOS is in the super threshold region. So somehow we have to push the PMOS strength lower and NMOS strength higher. That is basically what you have to do. Right. So that is the problem statement which this paper tries to address. So we'll just focus on this particular solution. There is another proposal for doing this, and what they do is they use a diode connected PMOS in series out here. The diode connected PMOS M5 and M6. You see, you still have the cross coupled M3 and M4 as before, but then you have a diode connected M5 and M6, which helps to reduce the drive current of the PMOS. That's basically what they do, and they help to make this work even from subthreshold to superthreshold. This is again some work proposed by some other authors, not these authors. But there are some again drawbacks with this particular approach, and I'll kind of leave it to you to just go through the text to see what the drawback is. It's kind of discussed out here, but I want to come back to the proposal by these authors. So what they do is there was another work which they reference, where basically what they do is they have a series of these cross coupled level converters. Okay, when I want to go from say 200 millivolts to 1 volt, I will have multiple of these same topology, the simple level converter which we saw before. You will have a cascade of them, but each one will be using a slightly different power supply, higher and higher supply, so that progressively you do the level conversion and you don't have this problem of having to overcome a very large voltage difference. So that is again not very practical. I mean, conceptually it is fine, but not very practical because of having to supply all these different voltage levels to all these stages. So instead, what these people do is they use this two-stage level conversion, and you see this level converter is the same. The topology is the same. M1, M2 and M3, M4 is cross-coupled. Similarly, M6, M7 are the inputs, and M8, M9 are cross-coupled. Except the first stage is being supplied by a diode connected NMOS. That way, what happens is this voltage here is one diode level down. When we say diode, it's a transistor MOSFET based diode. When you connect the gate and the drain together, it basically is like a diode. So you have one VT of the NMOS lower than VDD. So you are effectively creating internally a lower supply for the first stage without having to get it from outside. And in addition, what they do is they weaken the PMOSs here, M3, M4 and M5, by using high threshold transistors. Typically in modern processes, you will have transistors with multiple different thresholds available for you. So as a circuit designer, you have to figure out, besides sizing, what threshold voltage you want to use for which transistor in your circuit. So here, by using high threshold out here, or rather to put it another way, for M1 and M2 they use low threshold. So they are increasing the drive strength of M1 and M2 by using low threshold, whereas all the others they use the normal threshold, which is a higher threshold voltage. So that is another thing they do. And finally they do some sizing optimization of M1 and M2 so that the drive strengths of M1 and M2 overpowers the drive capability of M3, M4, even when the voltage levels are even when the input voltage level is very low. Okay, so that is basically what they do. So yes, so another technique is also, the question which is being asked is, can we use body bias to somehow modulate that? And body bias is also another technique where you can use the body bias for the M3 and M4, because finally you want to strengthen the pull down NMOSes and weaken the pull up PMOSes somehow. So all possible ways you can explore, and if you have the knobs to adjust body bias, that would be another way to adjust that.
If the normal potential is low VT device and high VT for PMOS.
Correct. So the question is, just low VT by itself doesn't it suffice? So this graph answers that. So what they have done here is that they have broken down the contribution of each of the techniques. So there is this is the original circuit where what they are plotting is the on current of the NMOSes, the pull down the NMOSes, and this one out here, D, is the strength of the PMOSes, pull up PMOSes. And we want to swap these two, right? We want to make the NMOS stronger than the PMOS. So what they do is, by changing this from low VT to high VT, by everything is high VT, but just the NMOSes they change to low VT. It does help push up the drive current, but it's not sufficient to cross. In addition, what they do is they increase the sizing. How do they increase the sizing? By simulation they try different sizes, and when you increase the size, what happens is that the first stage is the delay to drive the signal to the first stage, because there is some other inverters which are driving this, right? That inverters are kept fixed, but this stage, the first stage, basically is being driven by some circuitry out here. This circuitry size is kept fixed, but as you increase the size of these, this delay increases, but the delay of this decreases. So then you find what is the sum of the delay, where it comes to be minimum, and they plot this graph, and from there they pick a certain width which helps them to improve. They increase the size of the NMOSes such that the drive strength increases further, but still it is not crossing. But then when they put the diode connected NMOS in the top of the first stage, here M5, what that does is it reduces the voltage to the level converter, weakening these PMOSes further. And then when they do that, that allows them to they do two things. They increase the length of the channel length of the PMOSes, and then they do the diode connected devices. With that, they are able to make the drive strength of the NMOS bigger than the drive strength of the PMOS across process variation. You see, this is basically a number of simulations they have done to get that to get this spread, and across the process spread they are guaranteeing that the NMOS is stronger than the PMOS. Okay, so M3 and M4 have a W by L ratio that is substantially less than that of M1 and M2 to increase NMOS's ability to pull the output mode load. That is basically what they have done. Now one thing is, they, having done the design, they characterize the power and the delay and across different input supply voltages. So here, for example, what they are comparing is that as supply voltage reduces, the buffer, which is just a simple inverter, its delay goes up, which is what we expect. Remember, on this side it's log plot. Okay, the delay is really substantially reduced, whereas the delay of the buffer doesn't change much in the log plot. So it's kind of portrayed as if it's a positive thing, but if you really look at it, right, I mean, it's like you have a constant delay across different voltages, so it's a good thing. But on the other hand, really, how have you achieved that, right? You have achieved that by really slowing down your level converter delay at the higher voltages. So it's not necessarily a good thing, because if I have a design which is supposed to work well across a large voltage range, here you are unnecessarily penalizing, using this particular topology, the operation at higher voltage, because this level shift converter is giving a large delay compared to a simple inverter. Here the delay penalty is not much at low voltages, but at high voltages I have a large delay penalty. So it opens up again it opens up, shall we say, opportunity to think of a better design or a better way of doing it, because I don't want this. I want it to track the buffer delay because everything speeds up. So I would like even the level converter to speed up, not remain at the same delay. Okay, so the point I want to make is sometimes in these papers you have to read it such that you have to kind of look for issues, and despite the authors not pointing it out, there could be some aspects which might be important for certain applications. Now the thing is that when they do the analysis out here, you have to kind of analyze and look at what is the worst case condition for this level converter. Where is it going to break? Under what condition? Right? Whenever you do a design, you have to kind of look to see what are the weak points. How do you break the design? So when will the level converter break? It's when the NMOSes are not able to overcome the PMOS. So what process condition, what temperature condition will lead to that problem? NMOS has to be made weaker. That means you have to use a slow NMOS process condition. That means the NMOS thresholds are higher than what you expect it to be. Right? PMOSs have to be stronger than you expect it to be. So it has to be a fast PMOS. What temperature will you use? For that you have to look at the dependence of threshold voltage on temperature. As you increase the temperature, threshold voltage reduces. That means if I want to weaken the NMOS, I have to increase the threshold voltage. That means I have to use the lowest possible temperature. So that is the worst case condition. You see, in that condition, the minimum supply is 200 millivolts, whereas other conditions I can reduce the supply and it will still work. In addition to this, these people don't mention that, but the next paper will just see it does that. The supply voltage they use on the low side and the high side. The high side they use a supply plus 10% of nominal, so that you are benefiting the PMOS even more. And the low side, the supply uses 10% less than the normal. Typically, supply voltages are specified plus minus 10%. Of course, you can ask the question, is that justified? Okay, why would my supply on the low side, anyway why does the supply voltage even fluctuate that much? It's because your power supply is not able to supply the loads. Right? But if I am using a low voltage, and especially voltages at 200, 300 millivolts, there is not that much current. It's very easy to design power supplies to supply good voltages at that. So it might be overly pessimistic to assume that the supply voltage will drop by 10%. But nevertheless, whatever amount it drops by, you use that value on the low side and the higher value on the high side, in addition to slow and fast and the lowest temperature. That will be the worst case condition, and if you can ensure that your level converter works there, it's functional, then you have basically a good design. So now what they have done is they have taped this out in a chip. This is a microcontroller which uses the low threshold, and then this is some UART interface which uses nominal voltage, and they have some interfaces out here. And then they basically what they do is they make some measurements out here. So this is from the measured, and the measurement and simulations seem to match well, which means the process models are pretty good. But before that, I wanted to there's another interesting point. Basically, the size of the level converter is 16 times size of the minimum standard cell inverter. So it's kind of big. The level converter takes up area. It's not just size of few inverters, but it's much bigger than that. And they talk of some technique to extend the range further down below 200 millivolts. That means, what does it mean? The level converter itself is able to handle 200 millivolts to 1.2 volts. But if you want to go even further down to maybe the input on the low side, you want to operate at even lower voltages, maybe 100 millivolts or so, then with further modifications, which they talk out here, simple modification, which I'll let you read up and figure out what it is, you can extend the range. But one important point is that this technique is not typically needed. That means I don't need to extend the range beyond maybe about 200 millivolts, because many studies have shown that the optimal point of operation is about 300 millivolts. This we'll discuss later in the course, where we had also alluded to maybe in the last semester, where if you reduce the voltage too much, things become so slow that the static energy starts becoming dominating. So you don't want to operate things very slowly also. So that leads to a certain optimum voltage at which you want to use. Okay, so um, now there is another approach to that. The idea is, the problem is still the same. Okay, the problem is that you want to overcome, you want M3 to overcome M5. That is a challenge, right? And you have to weaken M5. And this is a paper by these authors from Germany, I think. And what they essentially say is that just by sizing and increasing the size of the NMOS is no good because of the exponential degradation. The size also has to grow up exponentially. They find that they have to increase it by 2400 times, which basically makes pure sizing based approach not practical. So they contrast their approach with another approach, where what this approach does is it's again they refer to this approach where the idea is you have this basic cross coupled structure, but then you put a current limiter in the top, right? If you have taken the analog course, maybe most of you have taken the basic analog course, you will see that this is a standard current mirror. So you have a current here generated, diode connected PMOS, which supplies a voltage to these two gates. So this voltage will be not ground, somewhere in between, and that reduces the currents which can come from here. So that means once I limit the current which can come through the PMOS, that is what I want. I want to limit the current through the PMOS so that NMOS can overcome that current when it's on. So this is the approach with which they contrast. The drawback of this approach is pretty obvious. I have this current reference which is always on, right, which is not good. So to deal with that, they have this proposal where they embed in some sense this current source on the top out here, right? So there is this kind of cross coupling happening, but it's kind of looks a little weird. In the analog circuit, perhaps you might have seen this is also called a Wilson current mirror. But again, the idea is the same here. You can go through the way it works. When this M6 limits the current through the M5, and what that does is it helps M3 to overcome M5. And also the way this is set up, you don't have, once the system stabilizes and reaches its logic values, there are no more static currents out here. Okay, so you can kind of just go through that and kind of see how that works. So so here, for example, they compare the performance of their circuitry and the energy consumption of the circuit of their approach, which is the lower one, versus the current mirror approach. And what is interesting here, you see, is that the energy per level conversion, right? It reduces as you reduce the input supply voltage, but then it starts going up. Okay, that's because things become so slow at these very low voltages that you're dominated by the leakage energy. And this is something we'll see again and again with energy, minimizing energy, where there's optimum voltage at which energy is minimum. Here is another kind of interesting thing to see, is that they have characterized their level converter, the delay of that across voltages for 3 different process conditions. And you see at these low voltages how much spread there is. And you see this is actually a log plot. You can be orders of magnitude away. Right? So that is one of the challenges of very low voltage design, is that the variability, process variability, will lead to very large performance changes. So that is something one has to basically work with in some sense, or have a way of addressing that. Okay, so one way of addressing that is basically to use different voltages. You have to you don't have static voltage scaling, but you have to allow for either what is called adaptive voltage scaling. That means the voltage what is used really depends on the process condition. Right? That is what adaptive voltage scaling is, and the adaptive voltage scaling essentially will have a way by which somehow you sense what is the process condition and adjust the voltage so that For example, something like this, if you are on this curve, you use a higher voltage. If I want this delay, then I use a voltage which is higher, so that I still maintain that delay. And what is shown here is the spread of the delay. It's like you can say the histogram of the delays. There are multiple, they do a Monte Carlo analysis where you simulate and measure, and it has a log normal distribution. What is log normal distribution? Log normal is when the variable of interest is related to another variable which has a normal distribution via exponential. So current is exponential to the threshold voltage. Threshold voltage is normal distribution. And delay is inverse to current, so delay is also exponentially related to threshold. So when that happens, the delay has a log normal distribution, and these are the parameters. So they compare their approach versus the previous approach and essentially see how well it works. So this is where, again, how they compare. The worst case condition is slow NMOS, fast PMOS, VDD low side is made lower, VDD high side is made higher than nominal, and use a low temperature. And they use a temperature of minus 40 degrees. Okay, their circuit is supposed to run from minus 40 to plus 125. So military grade operation, you have to use these larger spreads. Okay, so I'll basically stop here. You can go through both these papers, and if you have any questions, we can discuss that in the next class.